In 1950, the final Rolls-Royce Merlin rolled off a British production line, marking a sudden and profoundly quiet end to the most famous mechanical voice of the 20th century. For over a decade, this 27-liter supercharged V12 aero engine had been the undisputed heartbeat of national survival. It was the power plant that lifted the Hawker Hurricane, the Supermarine Spitfire, and the Avro Lancaster into the sky. Across shadow factories in Derby, Crewe, and Glasgow, a relentless industrial network had cast, machined, and assembled more than 160,000 of these aluminium blocks to feed an insatiable wartime demand. Yet, almost the moment the final engine was crated, the Merlin was rendered entirely obsolete. The mechanics who knew every torque setting, every oil leak, and every vibration of this V12 suddenly found themselves maintaining legacy equipment on damp grass airfields that still smelled of high-octane aviation fuel and hot glycol. The deafening, percussive thunder of piston power was rapidly being replaced by the smooth, high-pitched scream of the early gas turbine. The jet age had arrived, and it did not require the heavy, complex mechanical brilliance of a liquid-cooled piston engine. This was the paradox of Britain's greatest power plant. The Merlin had not failed. It had not lost its power, its durability, or its legendary status among the pilots who had trusted it with their lives. It was simply overtaken by the ruthless march of technology and the absolute limits of physical speed. The engine that had saved a nation could not save itself from the future. But the real story of the Rolls-Royce Merlin is not only the story of its final day on the factory floor, or its rapid displacement by the jet. It is the story of how a single block of metal became the physical, undeniable sound of British engineering pride, and what happens to an industry when that sound is forced to become a memory. Every week, we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in Derby in 1933. In the early months of 1933, the British aviation industry was standing on the edge of a precipice it could not fully see. At the Rolls-Royce works in Derby, the atmosphere was thick with a mixture of mourning and intense industrial pressure. Sir Henry Royce, the uncompromising engineering patriarch of the company, was in the final months of his life. But nostalgia was a luxury the factory floor could not afford. The air above Britain was changing. For years, the Royal Air Force had relied on the Rolls-Royce Kestrel, a brilliant but aging V12 that had powered a generation of silver-doped biplanes. However, across Europe, aircraft designers were shifting toward heavier, all-metal monoplanes. To drag these new machines through the sky, Britain did not just need a refined Kestrel. It needed a colossal leap in brute force. It needed an engine capable of breaking the 1,000 horsepower barrier. The problem was that the British government was not initially willing to pay for it. In an era still defined by peacetime budgets and economic austerity, the Air Ministry hesitated to fund a massive new, liquid-cooled engine program. The decision that followed in Derby would change the course of the 20th century. Driven by figures like Ernest Hives, who understood that an engine company without a future power plant was already dead, Rolls-Royce decided to fund the project themselves. They called it the PV-12, standing for private venture, a bureaucratic name for a monumental financial risk. The PV-12 was conceived as a 27-liter V12, a 12-cylinder engine with its cylinders arranged in two banks in a V shape, displacing exactly 27 liters of volume swept by its pistons. To understand the sheer scale of this machine, one must look at the foundry floor in Derby. This was not a delicate automotive motor. The block, the massive main engine structure that holds the cylinders and endures the violence of combustion, had to be cast from aluminium alloy, combining lightweight properties with the strength to contain thousands of controlled explosions every minute. In the foundries of Derby, the work was physically punishing. Men in heavy aprons poured molten aluminium into intricate sand molds, a process where a shift in temperature of just a few degrees could result in a porous casting that would inevitably fail under the stress of flight. Once the block was cast, it moved to the machine shops, where rows of lathes and milling machines cut the metal to tolerances measured in the thousandths of an inch. The scent of cutting fluid and hot metal hung in the air as machinists translated ink drawings into physical geometry. This was the reality of British engine development. It was not a sudden stroke of genius. It was a brutal, exhaustive process of shaping metal by hand and machine. When the first prototype of the PV-12 was finally bolted onto an engine stand in a Derby test cell in October 1933, the results were sobering. The engineers opened the throttle, anticipating the roar of 1,000 horsepower. Instead, the testing instruments registered a modest 790 horsepower, a measurement of how quickly the engine could do work. It was a respectable figure for a lesser engine, but for a 27-liter block designed to define the future of British aviation, it was a failure. The engine was heavy, it was temperamental, and it was nowhere near the target. Worse than the lack of power was the lack of reliability. The early PV-12 suffered from a fundamental engineering flaw in its cylinder heads. The upper part of the engine that helps seal the cylinders and contains the valves. Rolls-Royce had attempted to use an evaporative cooling system, an overly complex design that proved utterly incapable of handling the immense thermal loads generated by 27 liters of displacement. Blocks cracked. Gaskets failed. The test cells in Derby regularly fell silent as mechanics were forced to tear down the hot, oil-stained aluminum, inspecting the shattered components to understand where the metal had surrendered to the heat. The mechanics who stood over those broken engines were learning a hard lesson about the limits of material science. The engineers in Derby abandoned the flawed evaporative cooling and shifted to a pressurized liquid cooling system using ethylene glycol, a chemical coolant that allowed the engine to run at much higher temperatures without boiling over. They completely redesigned the cylinder heads. They strengthened the crankshaft, the heavy rotating shaft that turns the violent downward motion of the pistons into smooth rotational power for the propeller. Bit by bit, the engine began to hold together. The power output slowly climbed up the testing charts, crossing 900 horsepower, and finally pushing toward the psychological barrier of 1,000. In 1935, the prototype engine was finally hoisted out of the Derby test cells, transported to an airfield, and bolted into the nose of a Hawker Hart biplane for its first flight. The sound that echoed across the damp grass airfield that day was distinctly different from the kestrels of the past. It was deeper, more percussive, carrying a mechanical resonance that vibrated through the chest of anyone standing near the flight line. The Air Ministry, suddenly realizing the sheer potential of the private venture they had previously ignored, officially backed the project. Following the Rolls-Royce tradition of naming their aero engines after birds of prey, the PV-12 was given the name it would carry into history, the Merlin. Yet building a successful prototype was only a fraction of the battle. In the late 1930s, the shadow of conflict was lengthening across Europe. Britain was rushing to develop a new generation of fast, 8-gun monoplane fighters, the Hawker Hurricane and the Supermarine Spitfire. Both of these aircraft were being designed explicitly around the physical dimensions, the weight and the promised power of the new Rolls-Royce engine. The pressure on the Derby factory was immense. The engine line had to move from building handfuls of experimental blocks to a state of rapid mass production. Furthermore, the RAF mechanics who would eventually service them needed an engine that could be understood, maintained, and trusted on a windswept airfield in the middle of winter, not just in a pristine laboratory. The block was finally ready, but proving it in a test cell in Derby was not enough. It had to survive the brutal reality of a British airfield. To understand why the Rolls-Royce Merlin became a national obsession, one must first understand the physics of altitude and the brutal reality of the aero engine. An aero engine, an internal combustion machine built specifically for aircraft use, where power, weight, absolute reliability, and constant certification matter in ways completely alien to road vehicles, was not just a piece of hardware. In a British hangar, it was the ultimate arbiter of survival. It decided whether a Hawker Hurricane could scramble from a muddy airfield in time, whether a pilot could trust the throttle in a steep climb, and whether a ground crew mechanic could sign off a logbook without a shadow of doubt. By the late 1930s, the Merlin had evolved from its fragile early prototypes into a solid 27-liter Titan, but its true breakthrough did not come merely from strengthening its aluminum block. It came from forcing the engine to breathe. As an aircraft climbs, the air becomes thinner, starving the cylinders of the vital oxygen required to burn fuel. A naturally aspirated engine, one that relies solely on atmospheric pressure to draw in air, loses power precisely when a fighter pilot needs it most. The solution was the supercharger, a mechanically driven centrifugal compressor that forces a massive volume of dense, pressurized air into the engine's intake manifold. In the Merlin, this supercharger was driven directly by the crankshaft via a complex, high-tensile gear train. It spun at tens of thousands of revolutions per minute, howling with a high-pitched mechanical whine that perfectly underscored the deep, percussive exhaust note of the V12. This single device fundamentally changed the mathematics of the sky. By compressing the thin air at 15,000 feet, the supercharger tricked the engine into believing it was operating at sea level, allowing it to produce immense horsepower, the measurement of how quickly an engine can do work, where older designs would simply choke and stall. But forcing more air into the cylinders was only half the equation. To create a true industrial breakthrough, the Merlin needed a different kind of chemistry. In the years immediately preceding the Second World War, the Royal Air Force made a crucial logistical decision. They shifted their supply chains from standard aviation fuel to 100-octane petrol. This highly refined, knock-resistant fuel allowed Rolls-Royce engineers to drastically increase the engine's boost pressure. The sheer force at which the fuel-air mixture was rammed into the cylinders, without the engine destroying itself through premature, uncontrolled detonation. The combination of the reinforced 27-liter block, the high-speed centrifugal supercharger, and the vital supply lines of 100-octane fuel unlocked performance figures that had previously seemed impossible. The early Merlin II produced just over 1,000 horsepower. Within a few short years of relentless, high-stakes development, later variants were pushing past 300 and eventually up to a staggering 1,600 horsepower under combat conditions. Yet these numbers meant very little on a specification sheet in a Derby office. To grasp the reality of the Merlin's breakthrough, one must step onto a British airfield in the early 1940s, places like RAF Biggin Hill, Kenley, or Duxford, where the scent of burnt castor oil, hot metal, and high-octane fuel permanently stained the grass. Here the engine was not a theoretical marvel, it was a physical system that demanded relentless, skilled human labor. A mechanic working on a Merlin did not just see a beautifully cast V12. They saw a terrifying labyrinth of coolant pipes, ignition harnesses, magnetos, and oil lines. The carburetor, a complex mechanical device that mixes fuel and air before the mixture enters the engine, on a Merlin was an immense piece of precision engineering. It had to function flawlessly under extreme G-forces, preventing the engine from cutting out during violent maneuvers. When a Spitfire returned from a sortie, the engine block was searing hot. The mechanics, often working outside in the biting British winter or inside drafty canvas hangars, would strip off the cowling panels and plunge their hands into the cramped, oil-slicked engine bay. They checked the magneto timing, adjusted the valve clearances, and inspected the spark plugs for signs of running too lean or too rich. They drained the thick, black engine oil into pans, looking carefully for the microscopic shards of bearing metal that would indicate an impending catastrophic failure. This was the true strength of the Rolls-Royce design. It was incredibly complex, but it was fundamentally repairable by trained hands in austere conditions. It was a machine built for a service network that extended from the pristine machine shops of the Midlands to a frozen, makeshift field in Kent. The wear and tear on these engines was extreme. The heat generated by producing 1,300 horsepower from a 27-liter displacement tested the absolute limits of metallurgical science. Exhaust valves warped, gaskets wept under the immense internal cylinder pressures, and the supercharger drive gears endured punishing shock loads every time a pilot violently threw the throttle wide open. Yet the Merlin held together. It earned a reputation among pilots not just for its outright speed, but for its rugged mechanical dependability. It could take battle damage, overheat, vibrate violently, and still drag a crippled aircraft back across the English Channel. This trust transformed the Merlin from a mere power plant into a cultural icon. It became the definitive sound of British resilience. When citizens looked up and heard the unsynchronized heavy drone of a bomber formation or the sharp, tearing roar of a fighter, They were not just hearing internal combustion, they were hearing an industrial promise. They were hearing the result of thousands of hours of machining, casting, assembly, and maintenance, all funneled into 12 cylinders of screaming metal. The engineering had solved the problem of power, but Britain now faced a problem of scale. They needed the sound of the Merlin everywhere, all at once. By 1941, the Rolls-Royce Merlin had ceased to be merely an engine. It had become the mechanical heartbeat of a sprawling, nationwide industrial empire. The original Derby works, where men like Sir Henry Royce had once insisted on bespoke, hand-fitted craftsmanship, was no longer sufficient. Britain was fighting a war of attrition in the air, and survival required volume. The solution was the Shadow Factory scheme, a massive decentralization of British manufacturing designed to produce power on an unprecedented scale. Rolls-Royce expanded its engine lines into huge new plants at Crewe in Cheshire and Hillington in Glasgow. The Glasgow factory alone would eventually push out over 23,000 Merlin engines, a staggering figure for a power plant of such immense internal complexity. Inside these vast assembly plants, the culture of British engineering fundamentally changed. The traditional skilled fitter, who might spend days perfectly matching a single set of valves, was joined by thousands of women who had never set foot on a factory floor. These new machinists operated lathes, drills, and milling machines, cutting raw aluminum castings to tolerances measured in the thousandths of an inch, shift after exhausting shift. The sheer logistics of feeding this production network were staggering. A single Merlin V12 required thousands of individual components: high tensile steel crankshafts, delicate carburetor floats, heavy-duty gaskets, and miles of ignition wiring. Foundries across the Midlands poured metal day and night. Parts suppliers in Birmingham and Coventry were pushed to their absolute limits, sending crates of components northward to the final assembly lines. At its peak, the British manufacturing base was producing hundreds of these 27-liter Titans every single week. This scale was not an abstract industrial achievement. It was an acute matter of physical necessity. In a Britain where an engine could decide whether an aircraft lifted from a grass airfield, a lorry made its delivery, a motorcycle carried a rider through the night, a bus left the depot, a racing car survived the next lap, or a luxury car kept its silence at speed, power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and trust. As the demands of flight evolved, the engine had to evolve with it. When the air war pushed higher into the freezing stratosphere, the original single-stage supercharger began to lose its breath. Rolls-Royce engineers responded with the Merlin 61, featuring a two-stage, two-speed supercharger. This was a highly complex mechanical air pump that compressed the thin atmosphere twice before forcing it into the cylinders, complete with a liquid-cooled intercooler to stop the intensely pressurized air from igniting prematurely. This single engineering leap reclaimed the high-altitude sky, allowing the Supermarine Spitfire to outclimb its rivals. But it also added terrifying complexity to the assembly line and the mechanic's toolkit. An engine built in Crewe would be loaded onto a train, transported to an aircraft assembly plant, bolted into a Lancaster bomber, and ultimately delivered to a windswept airfield in Lincolnshire. There it entered a completely different system. It became the responsibility of the RAF ground crews, young mechanics who relied on oil-stained service manuals and sheer instinct to decipher the temperamental nature of the supercharged block. They worked in drafty canvas hangars, their hands freezing as they safety-wired bolts, replaced fouled spark plugs, and hunted for microscopic coolant leaks in the dark. The factory had built the engine, but it was this vast, unseen network of workshops, parts bins, and freezing mechanics that kept the thunder of the Merlin alive, pushing the piston engine to the absolute limits of its physical design. The demand for the Rolls-Royce Merlin was so absolute that it fundamentally reshaped the British industrial landscape. The engine was no longer confined to the noses of agile fighter aircraft. It had become the heavy-hauling power plant of RAF Bomber Command. When the Avro Lancaster entered service, it required 4 Merlin engines just to lift its massive payload off the runway. This exponentially multiplied the strain on the British supply chain. A single heavy bomber squadron required dozens of spare engines, hundreds of replacement magnetos, thousands of spark plugs, and an endless stream of high-octane petrol to remain operational. At bomber airfields across Lincolnshire and Yorkshire, the evening ritual of starting the engines became a visceral, physical experience. The ground crews would plug in the heavy trolley accumulators, large external battery carts, to crank the massive 27-liter blocks. The engines would catch with a violent bark of blue exhaust flame, settling into a deep, vibrating idle that shook the earth. When a major raid was launched, the combined sound of hundreds of Merlin engines running simultaneously at full throttle created a low-frequency roar that rattled windows miles away. For the British public sitting in darkened homes below, that specific unsynchronized harmonic drone was not just noise, it was the definitive acoustic signature of the nation fighting back. But maintaining this immense fleet required an industrial aftermarket that rivaled the original assembly lines. The life of a combat aero engine was brutally short, running continuously at high boost pressures, enduring the extreme thermal shock of freezing altitudes in the searing heat of combat power. A Merlin had a limited operational lifespan before it required a complete overhaul. A major service process where the engine is taken apart, inspected, and rebuilt to strict factory standards. Engines were pulled from airframes covered in oil and carbon, bolted into wooden crates, and sent to sprawling civilian repair organizations scattered across the country. In these vast utilitarian sheds, mechanics and civilian fitters tore the engines down to their bare aluminum castings. They measured the steel crankshaft journals with precision micrometers, checked the connecting rods, the high-stress parts that linked the pistons to the crankshaft, for microscopic fatigue fractures, and replaced the heavily worn bearings. Bins full of discarded exhaust valves and scorched gaskets piled up in the corners of Midland's machine shops. The repair network became so vast that it absorbed local garages, motor factors, and light engineering firms that had been building road cars and commercial lorries just a few years earlier. The engine's sheer adaptability also meant it found its way into machines that defied traditional aviation logic. The de Havilland Mosquito, a twin-engine bomber constructed almost entirely of wood, was paired with two Merlins to create a machine so fast it could simply outrun enemy fighters without needing heavy defensive armor. The engine was proving that if an airframe was designed efficiently, the immense torque, the raw twisting force that drives the propeller, of the Rolls-Royce Merlin V12 could solve almost any tactical problem. The scale of the requirement eventually outstripped even the combined might of Derby, Crewe, and Glasgow. The British government was forced to look abroad, licensing the engine to the Packard Motor Car Company in the United States. While Packard brought American mass production techniques to the design, the soul of the engine, its complex supercharger mathematics, and its fundamental architecture remained strictly British. By the end of production, over 160,000 Merlins had been built worldwide. By 1944, the British-built Merlin had reached its absolute developmental peak. The late-stage variants, equipped with highly complex intercoolers and advanced fuel delivery systems, were producing over double the horsepower of the original 1933 prototype, all without changing the fundamental 27-liter displacement. It was an astonishing achievement of metallurgical endurance. The engine had survived the war, it had survived the immense pressure of mass manufacturing, and it had survived the brutal hands of freezing mechanics working on muddy flight lines. It was the zenith of British piston engineering. Yet the very moment the Merlin mastered the sky, the rules of aviation power were permanently rewritten. The first crack in the Merlin's absolute dominance over British aviation did not appear when the engine was old. It appeared in March 1943, precisely when the 27-liter V12 was at the zenith of its industrial glory. At a heavily guarded airfield at RAF Cranwell, a radically different shape took to the sky. The Gloucester Meteor. It had no propellers. It had no heavy cast-iron cylinder liners or complex supercharger gear trains. Instead, it was powered by early gas turbine engines, burning paraffin and producing thrust purely through continuous high-speed gas flow. The Meteor was a small crack, but it was a fatal one. It proved that the fundamental architecture of the piston aero engine had reached a physical, insurmountable wall. To understand why the Rolls-Royce Merlin began its long decline, one must understand the absolute limits of mechanical violence. A piston engine, where heavy metal pistons must violently stop and reverse direction thousands of times a minute, can only be spun so fast before the sheer kinetic energy tears the connecting rods apart. Furthermore, a propeller driven by a Merlin begins to lose aerodynamic efficiency as the aircraft approaches the speed of sound. The tips of the propeller blades break the sound barrier, creating massive drag and destructive vibration instead of forward thrust. Rolls-Royce engineers knew they could not simply bolt larger superchargers onto the Merlin forever. The heat rejection required, the stress on the aluminum castings, and the octane rating of the fuel had been pushed as far as metallurgy and chemistry would physically allow. When peace was declared in 1945, the vast British industrial machine that had produced over 160,000 Merlin engines slammed into a brick wall. Military contracts were canceled overnight. The sprawling shadow factories that had run day and night were suddenly quiet. The Glasgow plant, which had churned out tens of thousands of engines, faced immediate and drastic restructuring. Thousands of machinists and fitters who had spent years perfecting the tolerances of a Merlin crankshaft were abruptly sent home. Rolls-Royce found itself with a magnificent, war-winning V12 that the military no longer needed in bulk. To survive, the company had to pivot rapidly to the commercial sector, attempting to push the Merlin into the emerging post-war civil aviation market. This transition revealed a brutal truth about the market forces of commercial flight. A combat engine is designed to prioritize absolute performance and altitude over operating costs and passenger comfort. When Rolls-Royce adapted the Merlin for civilian airliners, such as the Avro Lancastrian and the Canadair North Star, operated by BOAC, the British Overseas Airways Corporation, the very traits that made the engine a legend in a fighter aircraft became massive liabilities in a passenger cabin. The first problem was the sound. In a Spitfire, the unsynchronized roar of 12 short exhaust stubs was the sound of survival. In the pressurized cabin of a commercial airliner crossing the Atlantic, it was an unbearable, deafening racket. The Merlin's exhaust note, combined with the high-pitched mechanical scream of the supercharger, subjected civilian passengers to hours of exhausting vibration. BOAC found themselves marketing luxury travel while strapping their paying customers between four combat-derived V12s. The noise was so notoriously severe that crews often wore heavy ear protection just to endure the shift. Airlines were forced to install heavy soundproofing, which ate into the aircraft's profitable payload, and engineers desperately tried to design complex crossover exhaust systems just to direct the noise away from the fuselage. The second, far more systemic problem was Force 1: iron, aluminum, fuel, and manufacturing costs. The Merlin was a high-maintenance thoroughbred. During the war, the Royal Air Force had built a massive, state-funded logistical network to handle the notoriously short time between overhauls. A bomber squadron expected to replace engines constantly, accepting it as the price of combat. But a commercial airline operates on tight profit margins. They require an engine to stay bolted to the wing for thousands of hours without needing a major teardown. The Merlin, with its complex valve train, highly stressed supercharger drive gears, and demanding liquid coolant systems, simply required too much attention from mechanics. In a civil aviation maintenance hangar at Heathrow in the late 1940s, ground crews found themselves constantly adjusting magnetos, chasing glycol leaks, and performing rigorous inspections on blocks that were fundamentally designed for a short, violent combat life. The cost of keeping a fleet of Merlin-powered airliners in the sky began to eat into the business model of post-war aviation. The engine was perfectly capable of doing the work, but the economics around it were failing. Rolls-Royce themselves understood that the piston era was closing. Even as they tried to support the Merlin in civil service, their engineering resources in Derby were rapidly shifting towards Force 6, turbine displacement. The company was developing the Rolls-Royce Dart, a turboprop engine, a turbine engine that drives a propeller, which promised turbine smoothness, massive reliability intervals, and a complete absence of the heavy vibrating reciprocating mass of a V12. The British aviation market was quietly making its decision. The Merlin had taught Britain to trust an aircraft engine, but it had not solved what would happen when that engine became too expensive, too loud, and too complex to justify in a peacetime economy. The block was still solid, the engineering was still brilliant, but the commercial world was already looking for a quieter, cheaper way to cross the sky. As the 1940s bled into the 1950s, the Rolls-Royce Merlin found itself caught in a ruthless cycle of technological displacement. The problem was not that the engine had suddenly become unreliable or weak. The problem was that the fundamental definition of aviation performance had moved beyond the physical capabilities of internal combustion. Force 6. Electrification, hybrids, batteries, and software displacement, which in the context of mid-century aviation meant the absolute supremacy of the gas turbine, was not just a distant theory. It was a physical reality parked on the tarmac, burning kerosene instead of high-octane petrol, and requiring a fraction of the moving parts. The Royal Air Force, the institution that had essentially willed the Merlin into mass production, fundamentally changed its doctrine. Fighter command transitioned rapidly to jet-powered aircraft like the Gloucester Meteor and the de Havilland Vampire. These new interceptors could climb faster, fly higher, and achieve speeds that would physically tear a propeller-driven Spitfire apart. The mighty Lancaster bombers were gradually replaced by the English electric Canberra, a jet bomber that flew so high and so fast it initially did not even need defensive guns. As the military contracts vanished, the vast industrial ecosystem that had sustained the Merlin began to collapse. Force 2. Workshops, dealers, fleets, riders, pilots, and service networks, which had kept the 27-liter blocks running across the globe, fractured. The Ministry of Supply no longer needed tens of thousands of replacement magnetos, supercharger impellers, or exhaust valves. The smaller shadow factories and machining shops in the Midlands, which had spent years perfectly cutting gears and casting aluminium for Rolls-Royce, were forced to retool for peacetime products or close their doors entirely. Inside the main Rolls-Royce plants, the transition was equally brutal. The assembly lines that had once reverberated with the sound of piston engines being hot-tested were cleared out to make way for the Avon turbojet and the Dart turboprop. The skilled fitters who had spent a decade mastering the delicate art of setting valve clearances on a V12 had to learn a completely new mechanical language: compressor stalls, turbine blade creep, and combustion chamber temperatures. The company's survival depended on abandoning the very engine that had made it a global powerhouse. But perhaps the most tragic chapter of the Merlin's long decline was dictated by Force 1: iron, aluminium, fuel, and manufacturing costs. By the late 1940s, there was a massive global surplus of Merlin engines. Tens of thousands of these incredibly complex, highly engineered power plants were suddenly classified as obsolete military surplus. They were no longer viewed as miracles of British engineering. They were viewed as heavy, expensive liabilities. In breakers' yards and military surplus depots across the country, a brutal scrapping process began. Brand new engines, still sealed in their original wooden delivery crates, were sold for a few pounds each. Many were bought solely for their metallurgical value. The immense 27-liter blocks were smashed apart with sledgehammers, the high-tensile steel crankshafts separated from the alloy casings. Thousands of Merlins were unceremoniously thrown into furnaces, melted down to recover the raw aluminium to build household goods, caravans, and the next generation of jet aircraft. The ultimate symbol of British mechanical pride was literally being reduced to liquid metal because the economics of peacetime could not justify storing them. For the mechanics and ground crews who had spent the war freezing on airfields, keeping these temperamental beasts alive with frozen fingers and oil-stained service manuals, watching the engines being melted down felt like witnessing the erasure of their own youth. The physical objects they had trusted with their lives were disappearing. In 1950, the very last Rolls-Royce Merlin designed for aviation use rolled off the production line. There was no grand ceremony, no national moment of silence. The factory simply finished the batch, boxed the final engine, and moved on to the next turbine contract. The era of the British liquid-cooled V12 aero engine, which had begun as a desperate private venture in 1933, was over. The engine was still strong. The technology was old. The military contracts stopped. The supply chains broke. The aluminium was melted. The factories moved on. The jet age roared. The sky went to the turbine. The piston fell silent. The engine had taught Britain to trust a sound, but it had not solved what would happen when the world no longer needed to make it. The death of the piston engine on the Derby assembly lines did not mean the death of Rolls-Royce. The company that Sir Henry Royce built did not collapse into obscurity when the 27-liter V12 was retired. Instead, it executed one of the most successful, albeit painful, industrial pivots in British history. The mark survived, but its fundamental mechanical identity was permanently altered. The engineers who had spent decades perfecting the intricate dance of connecting rods, heavy crankshafts, and poppet valves threw their energy into the spinning, continuous flow physics of the gas turbine. The Rolls-Royce badge would go on to grace the Avon turbojet, the Conway turbofan, and eventually the massive Trent engines that power modern global airliners. Yet there is a strange footnote to the Merlin's industrial afterlife. While the sky was surrendered to the turbine, the 27-liter block itself stubbornly refused to die. Stripped of its complex centrifugal supercharger and its expensive aircraft-grade lightweight components, the fundamental architecture of the Merlin was cast in heavier iron and steel. Renamed the Rolls-Royce Meteor, this naturally aspirated variant was bolted into the hulls of British tanks, including the Cromwell and the Centurion. The engine that had won the air war spent the next 3 decades dragging heavy armor across the mud of the Cold War. The block survived by abandoning the very aviation market it had been built to conquer. Today, the original Aero engine exists in a completely different British ecosystem. It is no longer a mass-produced industrial product. It is a meticulously curated artifact. At places like the Imperial War Museum Duxford, the Shuttleworth Collection, and during the annual revival meetings at Goodwood, the Rolls-Royce Merlin remains the undisputed star of British preservation culture. Keeping one of these engines airworthy today is a monumental exercise in reverse engineering. The vast wartime supply chain of Midlands foundries, civilian repair organizations, and endless parts bins is completely gone. When a modern restoration workshop needs a replacement exhaust valve, a supercharger bearing, or a complex carburetor float, they cannot simply order it from Crewe. They must often machine the parts themselves from solid billet, relying on oil-stained analog service manuals that were originally printed 70 years ago. The mechanics who work on these engines today are keeping a dead industrial language alive, relying on touch, sound, and deep mechanical empathy to tune machines that were designed for a world of infinite state funding. But the effort to preserve the Merlin passes a crucial test. This is not merely nostalgia. A running Rolls-Royce Merlin on a damp British airfield today is a physical argument about a vanished era of mechanical trust. Modern aviation and automotive power is defined by the absolute absence of drama. Today's engines are software-controlled, heavily shielded, deeply reliable, and profoundly silent. They are black boxes designed to be replaced rather than understood by the people who operate them. The Merlin represents the exact opposite philosophy. It was visually complex, temperamental, and physically exposed. When it ran, it leaked oil, it vibrated, and it demanded constant, skilled human intervention. It required a mechanic to plunge their hands into the machinery, to read the color of the spark plugs, and to listen to the exact pitch of the supercharger drive. It reminds us of a time when national survival, speed, and industrial pride were not digital abstractions, but physical problems solved by men and women cutting aluminum and steel. Britain did not stop needing power. It simply stopped needing power that required so much brutal, physical effort to maintain. The turbine, the electric motor, and the software-controlled powertrain eventually won because they made economic and operational sense. They were quieter, cheaper to run, and easier to certify. But in gaining that effortless reliability, the country lost a very specific type of relationship with the machine. What vanished when the Merlin left the factory floor was not just horsepower. It was a network of foundries, machine shops, and freezing airfields that taught an entire generation of Britons how to trust a piece of engineering with their lives. The business model failed. The military requirement evaporated. The factories moved on to the jet age. But the sound remained. Somewhere in a British air museum, a Rolls-Royce Merlin sits silently under the lights, its aluminium dulled by time and oil, a cold block of metal that still remembers how to make the sky tremble. See you in the next video.